My name is Timur Bashirov, and this is the webinar that will be speaking about how one can migrate to using exabyte.io platform, migrating from the command line interface tools. And before we start, I'd like to go over a few important details. The goal of this seminar is to help users understand what exabyte.io platform is and how to benefit from using it. This is the second webinar series in a monthly recurring series of events. Now it's the third Friday of the month, and we are speaking about advanced topics. If you instead would like to learn about the basics of the platform, I suggest you join the first Friday of the month seminar for that. Every participant should be a registered exabyte.io user, and every participant will receive a copy of this presentation on PDF after we're done, so there is no need to take notes. This webinar is recorded and will be made available to everybody after we are finished. We encourage you to ask questions. Please use Zoom chat functionality to ask questions at any time. There is a dedicated spot in the webinar to answer those questions as they pile up. So please do ask questions when something is unclear. We will assume that the webinar attendee today is an experienced computational material scientist, familiar with tools like Quantum Espresso, VASP, or similar. We will assume that the user understands the basics of Linux and Unix operating systems, has an established set of scripts and input files to perform the calculations, and would like to know how to migrate these tools to the exabyte platform. In order to do that, there really are two options. The option number one is to entirely bypass the web interface and use alternative connection options to access command line environment and reuse existing scripts. And that's a very quick to implement option, right? All we have to do is just to connect to our infrastructure, and it's quick to start for anybody who have used command line before. But the downside of it is that this kind of approach is error prone and it's difficult to reuse this information. The second option is when user can adopt the exabyte platform approach and create the reusable entities like materials, workflows, and computation jobs. This takes some time to learn, and that's why hence this webinar. But once we have these materials and workflows created, they are reusable. We can apply this workflow for multiple materials, and we can track and have the data-centric approach to the problem. So we'll be speaking today about the platform infrastructure, and then we'll speak in details about the entities that we are working with, like the materials, the simulation workflows, and the calculation jobs. I will explain how to create each of these entities based on the existing scripts or existing input files. So let's start with a quick note as well. All webinar participants can request access to the webinar account. We will be using examples that are performed under this account's infrastructure, so you will be able to see this information for yourself. This account has command line features enabled for it, and during the webinar, we'll see recorded functionality instead of doing it live, but you can follow this presentation and see the data online. So the platform infrastructure looks like this. We have the web browser that connects to the web application, and there is a database that contains the results of the calculations, and the web application and the database are connected to the computational cluster. Then there is also an alternative connection method, as you can see here. It's called the login node. And if you zoom in on that part, we'll see that really there are multiple ways to connect to our infrastructure, and the blue parts correspond to the entry points. So there are 4 alternative connection methods. Alternative meaning that they are not based on the web browser. They're based on secure shell connection in the first case, and a web-based command line terminal, and a remote desktop session through which users can access a familiar user interface of Vesta, Expression, and other tools. We also have the fourth option of programmatically connecting to the platform through RESTful API, but we will not be speaking about it in this seminar. The topic for a separate discussion. So let's proceed and understand how we can enable the SSH secure shell connection. For that, we have to upload an SSH key, a public key. We have to generate the public and private key pair and upload the public key into the platform. And I will demonstrate how to do that. We have to navigate to the account profile. So click on your name, select the account preferences, and then scroll down to SSH keys. This option has to be enabled for your account. And then you just put some title explaining where this key originates from, human editable title, and upload the key itself, right? So once the key is there, you will see that once it turned green, it's ready to be used. Now, what we can do with the command line through SSH can also be done through the web. So we do not actually have to have an external SSH client. We can use the web terminal, which I will demonstrate in this video. So we can click on account name and click on the terminal session, which will open an SSH terminal in the browser. As you can see, there is a command line session that is convenient to copy files, for example. So here's files on my local disk. I can drag and drop them onto the browser window, and they will be copied into my home directory. As you can see, this file just got copied. All right, its content right now is available through command line. So I can, for example, edit the name of the file, and if I want to download it, there is a tool called exa-download that can download this file back into my disk after I edited it. All right, so that's how we do basic operations like upload and download the files using the web terminal. Now, the third option is to use a remote desktop, which can be started in a similar manner as the web terminal. So we click on our account on the right-hand sidebar and select a remote desktop session. And here it's a familiar graphical user interface session for a Linux CentOS operating system. So we can do all that this graphical user interface supports out of this remote desktop session. So for example, there is a set of tools that we have already pre-installed. That includes Vesta, Expression, P4WASP, and other convenient analysis tools. There is also a way to deal with the file system through the remote desktop session. And there is a terminal session and the Files Explorer, as you can see. It's convenient to understand what the file system actually looks like when we are connecting through some remote alternative connection methods, right? And here we have to understand the key concept. And the key concept is that the login node that we are connecting into is in fact further connected to the computational clusters. The computational clusters contain a master node and compute nodes. And they are connected into the login node under the cluster 00 number. So for example, this is cluster 001. It is connected and is mounted on the login node under cluster -001-home. So if my username is Timur, under /cluster 001-home Timur, I will see the content of home Timur on cluster 001. And we on purpose designed that in this way because clusters can be hosted on different cloud providers. So by using different clusters, users automatically can get access to different kinds of infrastructure and computing hardware. And so all the three connection methods that we just discussed, the SSH, web terminal, and the remote desktop, they all connect into this login node. And once we do connect to it, we'll see inside the home folder links to cluster 001 and cluster 007 home folders. So for each user, we have multiple home photos on the clusters, and they are linked into the login node. And if we click on one of them, we'll see that there's some further subfolder structure inside the cluster 001 home. And we have links to organizational accounts where user is a member. For example, I am a member of exabyte-io account, organizational account, and I see a link to each home folder inside mine. We also have a data folder where web-based jobs data is organized. So if I run calculations from the web, I will find these calculations arranged inside this data folder. And we also have links to the Dropbox folder and templates for command line job scripts. So the job script templates is where we have the job scripts, and Dropbox is the cache, the unified cache storage, which is similar in concept to the Dropbox that is, everybody's familiar with, right? The Dropbox folder is connected to all parts of the infrastructure. It's available on the web, it's available on masters, it's available on login node, and it's meant for people to reuse small data. So things like scripts, pseudopotentials, or Jupyter notebooks, they can be accessed from multiple parts of the infrastructure. You can upload them using the web interface to access them on the infrastructure and vice versa. It's not meant for running calculations inside it because there are certain limitations on the side, on the speed of the file system there. But it's perfect for sharing small source code, pseudopotentials, and things like that. Now, when we do connect to the data folder, we'll see that there is a certain structure that this data folder contains inside. And the structure, the naming convention, has to deal with how the jobs are arranged inside the web interface. Inside the web interface, the jobs are organized based on the project and based on the job ID and their names. So if I have an account for user Steven that has a default project, then the jobs for the default project will reside under the Steven-default directory. And if the job is named a new job November 11th, 2018, then all of this will be slugified or presented in a computer-friendly format, and it will be present inside the folder where these job files are contained. So when I run a calculation from the web, I can still find this calculation and its files inside the corresponding folder, inside the data folder of my account. And that's handy when we need to do some additional analysis that we might not be supporting on the web yet, but there are tools like XCrystal that can visualize the Fermi surface, for example. That's the functionality that we yet to add support for through the web interface. But you can already use the XCrystal through remote desktop to visualize Fermi surfaces based on the results on the data that is produced inside the job folder. Okay, so here are important notes about the remote connection. This is an alternative way to access the Exabyte platform. It can be enabled upon request. There are three options: the web terminal, remote desktop, and a secure shell connection. Remote sessions are connected to a login node with a separate home folder for each user. And home folder has links to directories for each of the compute clusters. Command line jobs must be submitted from within a cluster directory. So before we submit command line jobs, we have to navigate into one of the clusters. There is a variety of software packages available, both via remote desktop and via command line modules. It looks like we don't have any questions at this point yet, so I'll proceed to discuss materials. So here I will demonstrate how we can start from Quantum Espresso input files and migrate the materials data to the Exabyte platform. So let's assume we have a Quantum Espresso workflow that contains two files. the self-consistent field calculation and non-self-consistent field calculation NSCF, SCF and NSCF files that I'm demonstrating here. Both of them contain the information about material, and both of them have to have this information to be equivalent to each other. Now, what we will do here is we will migrate this information to create a material entity inside the exabyte platform. Right, so first of all, make sure that we have the content of the files ready. As you can see, the first one is the SCF calculation, the second one is the non-self-consistent field. Step one is when we make sure the content is intact, we understand the crystal structure of this material, and we proceed to open the materials designer. So we navigate to the account profile, click on the plus button to open materials designer, and we clone the default material to adjust it. So we clone the default material, we remove the original one, and we set up the name for this material, calcium, tungsten, oxygen 4, right, from PWSCF input. Right. Next, we set up the crystal lattice parameters from PWSCF files. So we proceed to set up the crystal structure, and the crystal structure is triclinic because if we will see that the iBraf option is set to 0 inside this file. We copy the cell parameters, and we, in this case, also need to convert Bohr to angstrom because Quantum Espresso is counting in Bohrs, and inside the platform we count in angstroms. So we set up the lattice parameters to their angstrom values. All right, and we need to make sure that we set them correctly. So ABC parameters need to be set. As we can see from the input file, the structure, in fact, all the angles here are 90 degrees of the structure, right? So that's what we do. We set up the lattice parameters and the angles and apply it to the structure. So now what happens is that we have the default content of the basis, which is inherited from the default material, which was silicon in this case. But we have set up the crystal lattice according to the input inside Quantum Espresso input files. The second step is when we set the crystal basis parameters using the PWSCF input. And so we close the crystal lattice dialog and proceed to migrate the basis information. Apologies. Let's get back to it. So we copy the crystal basis information. It's already in crystal coordinates here. So that's simple. If in case this information is in crystal units, in Cartesian units instead, what we can do here is we can switch to using Cartesian units instead of crystal inside this dialog. But for this demonstration, we just need to copy the file, the content of the basis and paste it here. All right. If we click anywhere else on the screen, we will see that the basis now is also properly set according to the content of PWSCF input file. We also see that we by default put constraint values. So 111 means that there are no constraint on the movements of these atoms. This is the default value. If you do need to constrain some of the movements of some of these atoms for relaxation purpose, for example, you can set it up here as well. All right. And the last part here is when we save this material. Now the crystal structure information is fully copied. We can proceed and select save, put a tag from PWSCF, click OK. And when this loader ends up spinning, we'll see that the operation is successful. Now, when we exit this materials design session, we'll see that the material calcium tungsten 04 from PWSCF is in fact created in our collection, and it is properly tagged with from PWSCF tag that we just created. Okay, so this is how we can migrate materials information into the exabyte platform. The second option is to use conversion tool online. For example, we have OpenLabel that is also hosted on cheminfo.org, and it can convert the PWSCF information to POSCAR. And by doing that, we can get the POSCAR file and upload it into the exabyte.io infrastructure as a file. I have explained that in Getting Started webinar, how one can upload structural information. We do not support direct uploads from Quantum Espresso today. That's why we would have to use one of these two options. Okay, now let's proceed and speak about the workflows. So migrating materials information is the first step before we can run a job. Migrating the workflow logic is perhaps a more involved step where we need to understand first what is the logic, what are the logical units inside this calculation workflow. And here again, we start with the two input files that represent the self-consistent and non-self-consistent field calculation. And these two really are the logical units in our case. So what we do is we go to workflows inside our account, and click on Create button to open the Workflow Designer, which is opened with a template empty workflow, right? So what we do then is we adjust its name to make sure we remember what is inside. So it's a new workflow from PWSCF input. And here is its first sub-workflow. So workflows are subdivided into sub-workflows, and sub-workflows further contain units. We will see how we can edit both momentarily, but here we name this first sub-workflow SCF and SCF, right? And we then proceed to add a unit to this first sub-workflow. We need to make sure that the application is as we want. It's Quantum Espresso, its version is correct. We are in fact using the right models here, the right pseudopotentials. And we proceed to click on plus unit, append to current. Here is our PW_SCF unit that is added by default. All right, now this unit has a certain flavor and executable associated with it. And the default flavor is SCF, so self-consistent field. Now we can navigate into this unit and adjust its content. We can either select a different flavor, which we will do for the non-self-consistent field calculation, or in our case, we are in fact dealing with the SCF calculation, so we'll keep the flavor, but we will need to migrate some of the input flags. For example, there is a keypoint directory flag, disk.io, and verbosity that we need to migrate from the Quantum Espresso input. Okay, so I'm replacing the verbosity flag with the new content, and I'm going through the system to do the same. The system name list, the electrons name list, and the rest of this file to properly copy the information, except for the part that is related to materials. The part that is related to materials, I'm not touching because the materials information will be fed to this workflow from the template data. So based on which material we are using when we create a job, this template data is different. So here you can see that there are certain information like the number of key points and the structural information about this material that right now is set to the default material, silicon FCC, just to demonstrate and preview this input file. So I'm not touching the materials information, I'm only touching the systems, electrons, and control name lists. Okay. So the SCF unit now is ready. And we proceed to add another unit to this workflow to repeat the same, right? In this case, we're adding a non-self-consistent field unit. So I'm adjusting the flavor to NSCF. And as you can see, apologize, let's go back. As you can see, when I'm adding this NSCF flavor, the properties that are extracted, so when I'm adding this NSCF flavor, the properties that are extracted out of this calculation also adjust automatically. Like there is no convergence electronic, which is extracted from PWSCF unit, and the properties and the monitors both adjust in this case. Right, so I'm copying the control system and electrons name list, and making sure that they both are equivalent in this case, and removing unnecessary name list from the template, previewing the file to make sure everything is as I wanted. And here we go. Now we have PWSCF and PWNSCF template input files already inside this subworkflow. Now this may look like a laborious procedure, right? To be able to have to go through the control and input control system and electrons namespace, but you only have to do that once, because once we have it set up properly, once we're using the template information from materials, we will be able to reuse this workflow for any material in the future. All right, so the next step and the final step in creation of the workflow is when we save it. I'm again tagging it to be able to find it easier in the future from PWSCF input, and I click on Save button at the top. All right, so here we see this SCF and SCF workflow. You see its tags, and when we open it, we can navigate back and see the content of its input files. Okay, so that's how we create a workflow from the PWSCF input files, a reusable entity within the exabyte platform. The second option is when we come in and do certain calculations, the exabyte platform has a concept of a materials bank and a workflow bank. So it's likely that some of the materials and workflows that we are dealing with, other users in the platform have already created workflows that do exactly what we need to do. So in this case, the SCF and NSCF workflow represents the band structure calculation. So what I can do is I can go and navigate to the workflows bank and search for the band structure calculation. And as you can see, there is already a workflow that somebody else had created. So I do not have to start from scratch and create subworkflow and workflow content. I can copy the workflow from materials bank and start with it as a template. I would still have to go and assert that the content of this workflow makes sense. And we endorse the use of curators. So if you click on these three dots and enable the creator to see who created this workflow, then curator's account is where our platform administrators add their content. So it's curated, we assert that these workflows have high quality. Okay, so we endorse the use of curators bank workflows. Now, as you can see, this band structure density plus density of state workflow is inside my personal collection. And I can navigate and adjust it just like I did before. All right, so these are the two options that we can use to migrate the materials and workflows information to the exabyte platform. I don't see any questions yet, so let's proceed to the jobs. And now that we have migrated, now we have materials information and we have the workflow information inside the platform, we can start and discuss the executing the simulations. And so really, there's again two options that we can use to execute the simulations, and we'll label them as CLI and UI. So we can either copy the files directly into the platform infrastructure through command line, or we can create the reusable entities. Right? Excuse me. So we'll speak first about the CLI scenario, and then we'll proceed to the UI option. This is the user home folder on a cluster, and here we see the JavaScript templates files, a folder that contains the JavaScript template files, bash scripts, and Quantum Espresso and Wasp example inputs. So there are two ways to quickly get to run a command line calculation. We can either use this JavaScript templates file, and the second option is to create a job batch script and the input from scratch. And this is what I will demonstrate. And for that, we can use the documentation tutorial. Right, so here we will need, again, the content of our input files, SCF and NSCF. And we will also need to open the documentation tutorial explaining how to run a CLI command line example, command line job example. Right? It contains the input files, it contains the job script, and we will be copying this content into our infrastructure. All right. Now, the first thing we have to do is we have to prepare the runtime directory and copy the input files there. So here I'm navigating to the Web Terminal session, and I see that there are multiple clusters available to me, multiple clusters. The ones in blue are active, the ones in red are discontinued. So now I'm navigating to cluster 001, and I also navigate into the seminar account to be able to use its allocation. So now I see there is a seminar folder that I'm in, and here I'm creating the calcium CAW04, the runtime directory for this calculation, and navigating into it. Next, I'm copying the NSCF and SCF files into the infrastructure by dragging and dropping them into the browser. And by default, the files are copied into the home directory on the login node. So they are copied into // And that's why I'm moving everything that starts with CAW04 into my current runtime directory. I see that there is an extra file, so I'm removing it. And now we have the SCF and NSCF files ready. The next step is to edit the input files to use the default pseudopotentials. And here we will need to open the copy-paste dialog, which we can do by clicking Ctrl, Shift, and Command at the same time by pushing those buttons. So first, what we do is we open the input file, and we see that we have to adjust the pseudopotentials because the pseudopotentials are not yet present, but we have a set of default pseudopotentials that we can use instead. Right, so I'm navigating, going back to the tutorial to figure out where the pseudopotentials are located. And I will copy the pseudopotentials to my current directory. Right? So we'll see that there is a certain naming convention that we employ, which includes things like the approach that we use, generalized gradient approximation, the type of functional PBE in this case, the origin of the pseudopotential itself, the GBRV pseudopotential set. And so by traversing this folder structure, we can understand how to copy the calcium pseudopotential into our folder. And the same thing we do for tungsten and for oxygen as well. So now inside this folder, I have the input files and the pseudopotential files too. I did not have to copy the files, I could have linked them, but for the purpose of the demonstration, to make it clear, yeah, I'm copying the files. Right, so next step is to adjust the atomic species name list inside the input file with the correct pseudopotential names. Okay, so now I have adjusted the SCF input file and I have copied the pseudopotentials. We have to do the same with the second file, the NSCF. So we proceed and we do the same with the NSCF input file. We put the correct atomic species information and the correct pseudopotential names. The next step is for us to create the job script and introduce the modeling logic there and put the accounting parameters. So what we do is we come back to the tutorial and copy the content of the batch script. We have to click on copy and go back to our terminal session, open a new file, vim job.pbs, copy, paste the content of the batch script, and adjust the batch script to use T so that we can see it on the output of the SCF on the screen, and at the same time save it into the file. Okay. Now we also have to, I'm simplifying the input files a little bit so that they're just called SCFN and NSCFN in this case. And of course, we have to introduce the actual logic of the calculation. So first we run the SCF part, and then second we run the NSCF part inside this simple workflow. Next, I need to substitute these variables that are put inside the template for this batch script by default, right? And I have to introduce my email that I'd like to get notifications at. I put similar at exabyte.io, I adjust the name of the job to make it more informative, and I adjust the calculation parameters if necessary, like the job queue, the submission queue, the number of processors per node, the number of nodes, the wall time for this calculation. So all of these are options for me to adjust here. To understand which project to use, I have to navigate back to my account and navigate into the project on the web, right? So here I'm inside the default project for my account, and I'm using the webinar account. So the accounting name for this project is seminar-default, and that's what I'm putting instead of the template variable. So I'm opening the job script again and replacing the $project with seminar default. Okay, so now I have a fully set up job script that will use the allocation, the compute allocation for the seminar account, and will feed the data to the default project on the web. Next step is to submit this calculation and track its completion. So I use qsub to submit this PBS job. I use qstab to see that the job in fact was submitted. So you can see that it's queued. There is another job that I submitted before in this demonstration. Let's ignore it. This is a new one, 68953. As we can see here, when we submit it, we get the ID 68953. I can delete the old one to make it clear. Right, and now I see all the output files when the job starts running. So here I can tail the SCF output file to understand when it's finished, or I can also use the watch command to periodically do that. Right? So when we wait for a few seconds, you see that the calculation is complete. The sixth and the optional step here is when we can view the parsed job in the web interface. What happens is by default, we parse the content of the job originating on the command line. And we attempt to put the properties that are extracted inside this job into the web interface. So if I navigate back to the default project here, I will see that there are two jobs. named CAW04 that originated on the command line. And we see that by looking at its application, we see it's a shell script, right? Because that's what batch job script is. If I navigate into one of them, I will be able to see the results. So there's a CAW04 shell that extracted certain parameters like the Fermi energy out of this calculation, the total energy, and even some other results like the band gaps. And I will be able to download and preview all the files that this calculation have extracted. Like, we can see there are pseudopotential files, there's a shell output, and there's some wave function files here too. Okay, so we can access the content of this job on the web even after we are done with this calculation in the command line. Why is it handy? It's handy because we can now share this job with another account in the platform. In the command line, it's difficult to do any kind of sharing. We have to deal with Unix permissions, and that could be difficult to enforce properly, especially with the security rules. So here in the platform, I can click on these three dots on the dropdown and then select share as an option. For example, I want to share this job with my personal account. So now I'm working under the seminar account, webinar account, and I'd like to share it with my personal account with Timon. So I click on my name here and add the read permission and close this dialog. So now when I go back to my account, my personal account, I will be able to see this job there too. All right, that's how we share a calculation. Okay, so now is the second option. We just discussed the command line jobs, running them on the exabyte infrastructure. Now we will do exactly the same by using the native functionality of the exabyte platform by using the entities. So step number 1 and 2 is when we create a material and we create a workflow that we have just covered early in the seminar. Step number 3 is when we create the job and select this material and workflow inside this job. So what we do is we navigate to the list of jobs and click on create, and we are shown the warning message saying that we cannot create a job directly from here. We have to navigate into the project. So we go back to the project, select the default project, so the job resides there, and then click on the plus button. Okay, we adjust the name of this job and click on this 3 dots in the header on the dropdown and go select materials. So here, again, this material have been previously created by us. So all I have to do is just to select it to apply it to this job. Select the item. So now we see this material that we earlier created. And now I go to the workflow tab and select the workflow that we have just designed. So this PWSCF workflow that we just migrated to the exabyte platform. Now I'm selecting it inside the job. All right, so now I have a job template with the right material and the right workflow. The second part, the fourth part in the whole series, the second part in the job series, is to inspect the workflow to make sure that it actually uses the correct content. So here I want to use the GBRV default pseudopotential, so all the pseudopotentials are properly set. Now I navigate into the PWSCF input file, and I see that there are certain parameters that are set by default. Like we use the k points per reciprocal atom concept, and we set the number of k points as a uniform grid based on kppra. So here what we can do is we can adjust the input file based on the desired numbers from the original input file. We see that the key points in the original input files were 4 by 4 by 2 and 8 by 8 by 6, right? So that's exactly what I'm doing. I'm going to the important settings, and adjusting the key point grids. So we can see that the dimensions of the key points can be adjusted inside of the form. In the important settings, we have important settings listed for each of the units. So PWSCF has important settings in key grid, and PWNSCF has important settings in key grid. This key grid is a variable that is made available to the template. And when we edit this form, the content of this variable is also changing. Right, so now after I have adjusted this variable, I'm adjusting the job name as well to remember that I have edited the key grid. All right. And I'm proceeding to the final step here, which is to set up the compute parameters. So here we have the flexibility to adjust the number of cores, the number of calculation nodes, and the clusters, and the calculation queues. So discussing and explaining all that, I think will take quite a bit of time. Really, what's important here is that for most calculations, the regular queues are the way to go. And we can either submit it to the ordinary regular queue or to saving regular queue. Right? Saving queue costs less, but it can be interrupted. The ordinary queue are permanent, they cannot be interrupted, but they cost a bit more. So I'm selecting the 18 cores on cluster 001, which is the recommended setup for maximum performance. And I'm selecting the notifications to be sent to me for any updates about this job, when it started, aborted, or ended. Okay, and then I'm clicking on the check mark in the header to save this job. Okay, so what happens next? They're directed back to the project web page, and I can see this newly created job in the pre-submission status, and I can see a quick summary of its parameters. Right? So next, I can select this job in the list and click on Run to submit it. What happens next is that the status of the job is changed to submitted. So it's sent to the infrastructure. The resources started to be allocated for it. And there's a message that the job will start within the next 10 minutes. Usually it happens faster, but we need to provision the infrastructure for it on the cloud. So if we continue to wait, we'll see that within the next 2 minutes, the job is started, in fact, and its status is changed to active. Now we can navigate into this job, we can open it and see the progress, monitor the progress of each of the units. So PWSCF has a convergence graph here, which shows us that the calculation, in fact, is proceeding in the right direction. The calculation is converging. This is especially important for larger supercells and for things like transition metals, which could be difficult to converge. And at the end, when the calculation is finished, the unit is turned green. So orange means it's still active, green means the unit is finished. So now we can proceed to monitor the second unit, PWNSCF part. We do that, and since it's a long calculation, it takes quite a while for it to finish. Speeding up this video. So at the end, again, this unit turns green as well, and the job is finished. When that happens, we see that together with the first 3 tabs, materials, workflow, and compute, for the finished jobs, we now have results and files. So if we navigate into the results tab, we'll see the results of the PW_SCF unit, which include things like Fermi energy, total energy, pressure, total force on atoms, and forces on each atom, stress tensor, and such. Okay. So now we have this PWNSCF part as well, which contains an additional property of the band gap, which in this case is 0. right? We can also navigate to the files and see all the files that belong to this calculation. And they are named according to the units. So PWSCF in is the input for the PW_SCF unit. PW_SCF out is the output for that unit. And accordingly, we have PW_SCF in and PW_SCF out. The pseudopotentials are inside the pseudo directory. The out tier contains things like wave functions and other auxiliary data for this calculation. The JSON file contains the original configuration routine that is used by our infrastructure software to set up this calculation. And .exabyte contains all other information that normally users should not need. It's a system folder that we use to run this calculation. It contains things like checkpoints. For example, if a user were to restart this calculation, it would not need to go from the beginning if some of the units are already completed. Okay. We can also go back to the compute tab and click on the cost of this calculation to see how long it ran for and what was the cost for running it. Okay. So here is the quick summary of CLI versus UI jobs, right? Command line interface jobs, provide a quick way to start, and it can be familiar to many computational material scientists already. But they require us to modify the input files every single time when we create a new job. And they can only store the data on disk. So there's limited presence in a database, there's limited collaboration that we can do. UI jobs takes some more time to get used to, but when implemented, they can deal with multiple materials at the same time. I selected a single material in this demonstration, but we can also select multiple, create multiple jobs. And automatically reorganize the data for these calculations in the database to enable the collaboration and further data analytics too. So most people use a limited number of workflows. And when we migrate the most important ones, like for the calculations of the electronic band structure or vibrational properties or some chemistry, we can reuse these calculations with minimal adjustments on a daily basis, on a weekly basis, whenever we need to run new calculations for new materials. Okay, that's the fundamental important value proposition of the entities inside the Exabyte platform. Okay, I think we are mostly done with the content for this presentation. I have one raised hand, Khalid. I'm gonna let you speak right now, Khalid. Please go ahead and ask a question.
Do you hear me?
Yes, please go ahead, Khalid.
Thank you for this very enriching presentation. In fact, I was asking myself about the difference between the CLI and the UI interface, as the user interface, like it will translate into commands. Like what's the difference? Is it just like the actual development doesn't allow the use of databases using command line, or like will it come later, or it will always be this way? Like if you want to work properly, you will always need to use the user interface.
I think the answer is we still have to develop the tools that will properly parse the workflows, right? So I demonstrated how we can actually get the information from this. If I go back here to the jobs example. So right here, we can actually get the information from the shell calculation, right? And we show it inside the web application. So we do attempt to parse the calculations that originate on the command line, but because of the sheer diversity and the number of examples, implementing a proper way to parse it, implementing some meaningful metadata addition to it is difficult. And that's why starting with the platform in the first place, so creating entities in the platform, and then using either the user interface, or I haven't spoken about it, but we can also use RESTful API
Yeah.
So people who like to use Python, for example, or who like scripting can, instead of going online and clicking on the buttons in the platform, they can use RESTful API to perform these tasks in a more programmatic fashion. So by doing that, we do get this data-centric aspect, the databasing aspect. But it is difficult to parse an arbitrary script to understand its logic. That's the fundamental complication.
Okay.
Does it make sense?
Yeah, sure. Thank you very much, sir.
You're very welcome.
Thank you.
Right, then I see Altaf as well.
Excuse me?
You have, I see Altaf raising the hand. Altaf, please go ahead. I'll mute Khalid. Raise your hand once more if you want to speak. Altaf, I think your microphone is muted, but you have the stage now. Please go ahead and ask a question.
Can you hear me, sir?
Yes, we can.
Hello? Okay. Sir, can we use Xregine using terminal? Sometime we need it for a short time to view, just to view input file, to confirm it, such that it is correct, yeah, something like that.
Absolutely. So I have demonstrated how to use the web terminal, but all of the same actions can be performed with any SSH terminal. So as I showed
yesterday I tried it, but it gave error message.
Okay, please submit the support ticket and we can understand exactly what happens. So when you upload the SSH keys, you should be able to use any terminal.
Okay.
Right, so like, for example, there's PuTTY or Mac terminal. All of this should be possible. All right. Please submit the support ticket and we'll look into it in more details. That's usually the best way to get help.
Okay, thank you, sir.
You are welcome. Any other questions? Okay, looks like not. So again, if you have any further questions, please feel free to contact us by through support channels. We usually reply into those pretty quickly. And thank you much for participating in this webinar. I will provide everybody with the PDF and the recording so you can follow it on your own time. And we'll be speaking again about getting started with the Exabyte platform in April. Thanks much, everybody, and have a good day. Stay safe. Thank you.